So you're about to start, or you've just started your A level. Do you know one thing that will get you ahead of the topics is being really, really confident with the AS content and know what to revise for each topic? Because every topic that you will study, or at least the most of them in A level, has some basics or some basic knowledge that you actually know already. So my tip is to revise the correct ASO topic before you cover the A-level topic at school. And that's what we will do today. We will look at the topics that you should revise for each more advanced topic. Let's get started. So let's start with physical chemistry, the topics that you will cover, and they are the same for all of the exam board. So these are the titles from OCR. But essentially, we have kinetic, which is rate, order, Arrhenius. We have the equilibrium, so Kc, Kp, acid, bases, and buffer, thermodynamics, so Born-Haber cycle, or in general enthalpy. But in A level, you will add also Gibbs and entropy, and then redox and electrochemistry, so the all of the electropotential calculation and so on. So, if we look at kinetic, let's think about what you know already from this topic, what you've studied before. You've studied rates. Okay, so my tip here is to revise everything that you know about rates. This will be really important. So orders and Arrhenius, it's a bit more, it goes a bit more complex, but you know already how to calculate the rate. Okay, so how to calculate the rate, which is by, you've studied before, changing concentration over time. So think a bit about that. I would like you to revise all of the concept of collision theory, because when you think about collision theory, this will and all of the factors actually that affect the rate of a reaction relative to the collision theory, because this will explain the shape of the graph that you're familiar with when you calculate the rate graphically. Okay, so for the topic of kinetic, make sure you're confident with the collision theory and with the experiment that you've done before on how to calculate the rate. So a little bit of math here. Okay. Then, if we look at equilibrium, we have the new topic would be equilibrium constant with gases. So there would be some new equations that they're relative to the amount of gases and how to calculate the kind of concentration of gas, let's say, and Kc for homogeneous systems. So those are things that you actually know. So if we think about the homogeneous system, homogeneous means the same state. So you know exactly what this means. That is the same state. So for equilibrium, well, it's pretty clear the topic that you should study before it's that you should revise, and this is the one of Le Chatelier principle and equilibrium. So very important that you revise Le Chatelier. And the factors, well, and also using Le Chatelier, you can explain the changes in equilibrium. But also very important in AS, you do Kc and how to write Kc and the units. So very important that you are super confident with how to write Kc and its unit, because all of the equilibrium constant that you come across, they will be written in the same way. Products over reactants for homogeneous system, including just the same, the components of the same state, okay? And the units works by canceling things out. Okay, so that's very important, because this will be fundamental and probably one of the most important things to be confident with also for this topic, acid bases and buffers. So when comes the time that in your A level you will do acid bases and buffer, please revise everything you know about Kc. I mean, Le Chatelier principle. So how the equilibrium counteract any change that is applied. And then again, the expression units are not so important in the case of acid and bases, but the expression is really important, maybe even how to rearrange it. So if you need to calculate one of the concentrations and you have the value of Kc, think about how you could rearrange it. This will give you very important preparation to study weak acids, but also buffers. And actually buffers, if you're confident in explaining Le Chatelier principle, and the changes that and how the equilibrium counteracts any change, you will be able to explain the buffer. Okay, so keep in mind this topic when you study buffer, because normally this is really difficult. And then, of course, you've studied before the basics of acids. So what I would suggest you to revise is a look at all of the equations that you've done before. So for example, acid plus a base, yeah, to give a salt plus water. Which bases do you know? Can you revise some of the common acids, some of the common bases? Okay, so that's the basic for this topic. Okay, or at least the things that you have done before in AS that you can apply to this. And trust me that this will give you a big jump start. Okay, and thermodynamics. So a lot of new things coming in A level, because you will have Born-Haber cycle, entropy, and Gibbs free energy. So entropy and Gibbs free, they're kind of different new concepts. The Born-Haber cycle, however, you can very closely relate it to what you've studied about enthalpy before. Okay, because with enthalpy, very important that you're confident with all of the definitions. Okay, so definitions, I mean enthalpy of formation, enthalpy of combustions, the cycle. Do you remember how to do the cycle and how to work out the equation that you need to use looking at the cycle? Okay, as well as bond enthalpy and calorimetry. All of these, what are not directly related with this topic, but sometimes in very open question they come all together. Okay, so very important that you're confident with that. And another thing that that was not actually just enthalpy, I would say, just to make sure you're confident with all of the definitions and the cycles. Enthalpy of formation, enthalpy of combustion, and bond energy. Okay. One more thing, the concept of endothermic, exothermic, and linked to that also the energy diagrams. Okay, that's a very important one to revise. So do you remember how to write the energy diagram for exothermic, endothermic reaction? Okay, those are the key things. And then lastly, we have actually redox and electrochemistry. So again, new calculations will come, you will come across. But I would suggest you to revise ionic equations for this. Do you remember how to write ionic equations? And you can link this ionic equation in the basic of the redox that you've studied before. So what I mean is the basic of half equations. Can you write half equations? Can you identify the oxidizing and the reducing agent in a redox? And of course, find the oxidation number. Okay, those are all very important because all of the rest of calculation with electropotential, cells, and so on, they will be based, of course, in this type of equations. Okay, so this is actually it for my help, and I hope you find it useful. So remember, study the basics and think about what you know already for each of these topics, because it will really get you ahead of your A levels. So let's go into more details on each topic for this A level transition. Okay, so the first topic that we looked at was kinetic. Okay, so one thing that I really want you to think about is how do you actually calculate the rate? Okay, so the graph here to remember is concentration over time. Okay, so normally this was concentration of a reactant or of a product, depending on the type of reaction. Okay, so here think about the physical changes or detectable changes in a chemical reaction that you can actually investigate. And normally it would look something like this. Let's say we're calculating the reaction of a reactant. The reactant would go kind of like this. Let's make it a little bit better. So it would go something like this. Okay, so I want you to think about and take a moment for that. Why is it a curve? Do you remember? And how do you calculate the rate? So the rate as an equation is actually change in concentration over change in time, which means that in this graph, it would be the gradient of the tangent. So this that starts at 0 is called, remember, the initial rate. Okay. And the rate, as you can see, changes across the reaction because notice that the tangent changes slope. Okay, so let's think about what that means. What it means is that the concentration of these, let's call it reactant, has an effect on the rate. But now I want you to think something else. Let's say that instead of this, you have the concentration of a reactant and it goes like this. I want you to think about, is the slope of this curve changing? Does this reactant affect the rate in any way? Yes or no? Tell me. No. It doesn't, because, as you can see, the slope is the same. So what this means is that this reactant has no effect on the rate. Okay? This will be important because if you understand this logically, then understanding what orders are will make sense. Because orders tells us the proportionality between a reactant and the effect that it has, or better, the change in concentration of a reactant and the effect that it has on the rate. Okay, so if, like in this case, just to tell you, the one before was called first order because the rate was changed with the change in concentration. But this, it's called a zero order, of the reactant, because it doesn't have any effect on the rate because the rate is constant. But anyway, don't worry about one, like first, second, and zeroth order, but just interpret this graph. Important. Okay. Then the second thing we talked about is collision theory. Okay, so this is important because when we have a bit more complex chemical reactions, the rate depends on the collisions, but it could be the collision of not all of the reaction, like not of, let's say, you've studied before actually, think about organic chemistry. And we see multi-step mechanisms, right? Because we have a first step and we have like one reaction. Then we have another step, like another curly arrow. So you actually have come across this multi-step mechanism before. And the collision theory is important because it tells us that the rate determining step, so the step that is the slowest in the chemical reaction, is the one that affects the rate. So collision theory, that tells us that so it tells us that the reactant have to collide with enough energy to overcome the activation energy and in the correct orientation will be just for this step that affects the rate. Okay, so here is just so that you've heard before this rate determining step. Okay, Arrhenius, don't worry about it, but what I want you to remember for that is the concept of activation energy. Okay, do you remember where we wrote activation energy? Well, it was this graph where we have the progress of the reaction and the energy changes. Okay, so remember, we always wrote it like this. This is for an exothermic reaction, but remember that the activation energy is always from the reactant to the top of the curve. Okay, remember what affects the activation energy? Catalyst, and then that is actually the only thing. Okay, so a catalyst would lower the activation energy. So for the Arrhenius equation, just be aware of this term and the definition because you will need, because it will actually be the equation to calculate that. Okay. So let's continue with the second topic for this revision. And the second topic is equilibria. Okay, so we said that the key concept to revise are the Chatelier principle, KC, and unions. So let's go into more detail in each of this. Okay, so let's start with the basic concept of equilibrium. So which reactions actually have or can form an equilibrium or exist in equilibrium. So we're talking about reversible reactions. Okay, so those reversible reactions, remember the ones that go in both ways. So we have the double-headed arrow. Okay, and very important that in order to have to reach equilibrium must be a closed system. So this means that nothing can enter nor escape the reaction. Very important. Then the equilibrium is reached when the rate of the forward reaction is the same as the rate of the backward reaction. Okay, so it looks like the concentration stopped changing. Not necessarily they're the same, but they simply stop changing. Okay, to quantify the equilibrium, we have the equilibrium constant. C is if we have a system where we can determine the concentration, but P would simply be the pressure. Okay, so K in general is the equilibrium constant. We will see it also in acid and bases. Yes, so just remember this K as equilibrium constant, and is always calculated as the products over the reactants. So for the products, we're determining like for Kc is the concentration. So we would write it as, so let's take this example, Kc being equal to the concentration of the product, which in this case is B, over the concentration of the reactant. Okay, so the value of this would tell us a bit where the equilibrium is lying. And this means, remember, lying on one side or the other, or shifting to one side or the other. It simply means that there is one, like the amount of that product or reactant is more or less or increasing. So equilibrium shifting to the right means whatever is on the right increases in concentration. That's what it means. So if Kc has a value bigger than 1, it means that concentration of B is bigger than concentration of A. So this tells us that the equilibrium is where, like right or left? What do you think? Right or left? If B is bigger, would be to the right. Okay? If Kc is smaller than 1, then means the opposite, that A is bigger than B. So the equilibrium would be on the left. So keep in mind this concept because it's fundamental for acid and bases. Okay, so keep this in mind, and then I will give you a little introduction for the acid and base topic. Okay. To work out the units, remember that depends a bit on what we're calculating, but in the case of Kc, we just simplify the units of concentration, which is mole per decimeters cube. Okay, so in this case, we have mole per decimeters cube at the top and mole per decimeters cube at the bottom, 1 and 1, so they cancel out. So it's also possible that it doesn't have any unit. Okay, so it simply works by canceling out the units. Okay. Then the Chatelier principle, the important concept is about the shift in equilibrium and how it counteracts the change, right? So this states that when a change is applied to a system in equilibrium, the equilibrium shifts to counteract that change. So what this means is that if we increase the temperature, the system will shift to decrease that back. Yeah. If we increase a concentration, the system will decrease that back. Okay, so I think the challenging thing really about the equilibrium to think about is about the temperature, because when the forward reaction is exothermic, the opposite is endothermic. So the thing to think about is that when the temperature is increased, that the change that we apply, the system would favor, what do you think, exo or endothermic to counteract that change? Would favor the endothermic because endothermic decreases the temperature. Okay, which means that the equilibrium will shift to the side of the endothermic reaction. Okay. I'm highlighting the temperature because remember that the temperature is the only one that changes the Kc value. Okay, so let's take this example of the simple reaction A to B. Okay, and the forward is exothermic and the backward is endothermic. So what we need to think about is if the temperature is increased, what would happen to Kc of this reaction? Take a moment to think about it. Always also like do it step by step, you know, this is a thinking project, the thinking process, because temperature increases. What does it favor? It favors the endothermic. Which side is the endothermic? Oh, is the backward reaction. So the equilibrium will shift to the left. If the equilibrium shifts to the left, which concentration increases? A. If this increases, and now it's not anymore like balanced, yeah? So this ratio between A and B changes. That's why Kc changes. And if concentration of the reactant increases, Kc would decrease, okay? I hope it makes sense. If not, make a note of it or rewind the video and think about the changes that mathematically could affect Kc. Remember, it's just the temperature, because the other factors like increasing concentration would, like the ratio between the products and reactant would stay the same. Okay, so that's the important part. And then we would get, I would say, into Kp and Kc calculations later on this year. For Kp, the only difference is that this is not concentration, but it's pressure. And here, to determine the pressure, or better, the like the concentration of a gas, we use the partial pressure, okay, which is the amount of pressure that each gas contributes in a mixture. And we will get into the calculation of that later on. But the concepts are really similar. We'll change just how we get to the partial pressure, okay? So I hope it makes sense. I'm going to save this one and let's move on to the next one, which is acid and base. So I wanted you to keep in mind for acid and base this concept of Le Chatelier principle and the equilibrium constant, okay? The reason is that for it's super important because of weak acids, and you will need to do a lot of calculation with weak acids. Can you remember the definition of weak acid? And maybe write an expression if you can. So weak acid, it's an acid, so let's call it HA, that partially dissociates. Partially dissociating means that it can set up an equilibrium. So the reaction doesn't go to completion, it means that it reaches an equilibrium instead. That's why we would write it like this. Very important to get used to this reaction. Can you write the K expression for this? And this, guess what? It's called Ka, because it's the equilibrium dissociation of an acid. Okay, same concept as Kc, same units of how to find it out, and so on. So here will be concentration of the products over the concentration of the reactants. The important part that just pretty much are things that you know already is that the value of Kc will tell us where the equilibrium lies. So will tell us the strength of the acid. Okay. In fact, if you think about the bigger the Ka, the more the equilibrium would be on the right-hand side. So would that be a stronger or a weaker acid? Would be a stronger acid because it releases more H+. Okay, good. So that's important. And the concept of Le Chatelier principle, well, it's a system in equilibrium. So that's very important. It will be linked with buffers because buffers maintains the pH. So guess what's that? It's equilibrium. Okay, so we will revise this very often again anyway. And in terms of basic of acid equations, so here practice and just remember the important acid and bases. Yeah, at least the ones common: hydrochloric acid, sulfuric acid, nitric acid. So all of these are the common one. And in terms of those are also all strong. Weak acid, we see many organic acids. So for example, ethanoic acid. Okay, maybe you want to write, do you want to try to write the expression or some equations with these common acids and ionic equations as well. For bases, common are all the oxides, hydroxide, carbonates. Okay, so nice practice for you would be to write some equations of common acids and common bases and the ionic ones. So ionic equation, if you remember, we can do it in different ways. You can either do the full equation and then split it into ions and then simplify it. It's super long. Because for acid and base reactions, really, the focus of the reaction is the neutralization product, which is water. Salt is not included because it would cancel out the ions. So for water, we can get to water with or from an H+ which is, of course, the acid, proton donor always, and then a base. And guess what a base could be? An oxide. But a base could also be a hydroxide. That would also form water. But a base could also be a carbonate. Okay? With carbonate, of course, we would have another product, which is carbon dioxide. Okay? And then, yeah, we need a bit of balance of this one, but it doesn't matter. Okay? And, okay. So that's the ionic equation, always useful to have them because when you do acid, base, and buffers, these equations will be very common. So you need to be really confident in just understanding the equation and so on. Okay, so I hope with acid and base makes sense. Let's look at the last part, which is thermodynamic, actually. We need to look and then acid and base. So with the thermodynamic, I would like you to revisit the definition of enthalpies that you've seen so far, which are pretty much just the enthalpy of formation, enthalpy of combustion, and bond enthalpy. Okay, those are the three definitions we've seen so far. What is important is the general cycle for enthalpy. Do you remember the ABC cycle? This is the reaction that we want to find the enthalpy of. And then we know that Hess's law states that the enthalpy of a reaction is independent from the path taken. So we can go A to B, or we can go A to B this direction. The difference is what is a C. In the case of formation, will be the common elements. Do you remember the definition of formation? The enthalpy change when 1 mole of compound is formed from its constituent element. So this is our formation cycle. Cycle important, why? Because it tells us the equation that we will need to use. Yes, so we know that the enthalpy change of this reaction would be the products, because that stays the same sign. Yeah, it could be exothermic, but it would stay the same sign, minus the reactant. Minus simply means change in sign. Combustion cycle, it would be the opposite. Yeah, and that is because you remember what is a C, or the equation for combustion is the enthalpy change when 1 mole of compound is completely burnt in oxygen. So it would be the common products, which means that the hours would now be going down. So can you guess the general equation for that? Would be now the reactants, same sign, minus the products. So remember, this general cycle are useful to work out the overall equation. And this is important because with thermodynamic, the Born-Haber cycle, it's simply like more steps of this cycle. Okay, entropy and Gibbs, they're different concept, a new concept, so we will see them when the time is due. Okay, for the bond enthalpy, we didn't do the cycle because there is an easier way to remember the definition. The important thing to remember is that bond breakings, you're breaking bonds, it's endothermic. Bond making is exothermic. So if we have a reaction A to B, we know that the reactants, we're breaking the bonds. So this is bond breaking. It would be endothermic. While the products is bond making, would always be exothermic. So the enthalpy of the reaction, it's found by the difference between these two. And the difference, of course, remember that this is a negative value and this is a positive value. Okay, so here I'm going to have a look at some of the example of actual calculations. Okay, but this is just the key concept. Yeah, and then the energy diagrams relative to also these endothermic, exothermic, it really depends on. So remember, endothermic was the energy change. So if this we have energy, and here progress of reaction, this is the energy change for an endothermic. We need to give energy, and the Products would have a higher energy than the reactant. Well, exothermic is the opposite. Yeah, so the energy goes down. I'm sure you remember this. Okay. So that's the thermodynamics. So when we look at more complex cycles, I want you to really remember this ABC cycle. Okay, trust me, that will help a lot. Okay, so I save this one too, and we look at the next one, at the last one, which is redox. Ionic equation, I actually just mentioned them because, well, sometimes the ionic equation can be constructed by looking at redox reactions. So here I want you to remember on how to write half equations and how we put them together. Okay, so, okay, let me see if I can, okay. So half equations, remember, for reduction, we have gain of electrons. So the electrons would go in this side, and normally we would form like a negative ion. Or could also be that we have, for example, something that is already positive, but it gains electrons and become less positive. Okay, so for the half equations, just remember reduction, oxidation, and just either think about the transfer of electrons or the change in oxidation number. While for oxidation, it's loss of electrons. So either something becomes more positive or, yeah, actually it's just something that becomes more positive. Okay, even more positive. So either look at charges or look at the change in oxidation number. Okay, and when you have an overall equation, let's take an example. X2 plus reacts with Y to form Y2 plus and X. Okay, can you identify what has been reduced and what has been oxidized by looking at the charges? Remember also that the charges are the same as the oxidation numbers. So 2 plus, this goes from 2 plus to 0. Either looking at the charges, oxidation number is the same. You can also write it as the half equation. So let me do this to make it a bit more clear. So if you write the half equations, you can also simplify like the transfer of electrons. So you see that if it goes from 2 plus to 0, what has happened? Oh, it gained 2 electrons. There we go, the half equation, and it tells you, oh, this is definitely reduction because it's gained electrons. While for Y, we go from, also this is the way to do half equation. Remember, Y to like looking at each element at one time and the change. So Y and Y2 plus, what has happened? Oh, has lost the 2 electrons. We write it on this side. So this is definitely oxidized. And remember that whatever is oxidized is the reducing agent because it causes the other thing to be reduced, while the oxidizing agent is reduced. So you know that whenever you find what is oxidized, what is reduced, so you can also find the agents by thinking in this way. Okay, good. I hope it makes sense. And oxidation numbers, there are different rules, and I would suggest you to practice a little bit more how to find the oxidation number, because sometimes you have a bit more complex examples. Yeah, for example, you have, I don't know, Cr2O7 2 minus. What's the oxidation number of chromium? Do you want to try to find it out? Oxidation number of chromium in this compound. Go for it, 30 seconds. So you know always the oxidation number of the other element if you're asked one element, which you can derive it by the periodic table. So we know is oxygen. We have 7 of them. So oxygen would contribute to the total charge of minus 14. You have an excess of 2 minus, which means that the 2 chromiums must be plus 12 to give the excess charge of 2 minus. But of course, you have 2 chromium, so each of it will be plus 6. Okay, hope it makes sense. Otherwise, let me know. We'll give you a bit more exercises to practice. So those are all the basics for I would say preparing for the new topics of physical chemistry. Okay, I hope it's helpful. If you have any questions, just let me know, and we will practice more for specific topics. Okay, thank you, and see you next time.